Hello, this is Math 2115 coming to you from the College U page for the fall of 2020, and this lecture is entitled Set Theory. The concept of a set is basic to all of mathematics, and it's a collection of objects. If the set is finite and not too large, we just can list the objects like this, but inside set builder notations. This is the set 1, 2, 3, and 4. We could also say that sometimes things get repeated, and so if I have the set A, 1, 2, 2, 3, 4, it is still the same set. If a set is a large finite set or an infinite set, we can decide it by listing a property necessary for membership. This is called the rule method, so we could say the set B is a set of x, such that x is positive and, comma, an even integer. And that's a set of all even integers, and we read that such that, and the brackets are called set builder notation. Sounds simple enough, but there are paradoxes and complications in deep mathematics. There's the barber's paradox. So suppose a barber shaves everyone who doesn't shave himself. Who shaves the barber? This is called Russell's paradox, or the barber's paradox, and led to quite a controversy because you see, you cannot decide if the barber is in the set or not in the set. Either way leads to a contradiction. This was resolved by a lot of heavy mathematics. We have the Zimmermann-Frankel axiomatization of set theory, and we won't really go into that. And this was a female author, so what they could have had as an easy solution, she said, was to make the barber a woman. Here's a problem for you to do. Using the notation that we just talked about, the set roster notation, answer these 4 questions. You know what to do. Let's see how you did. So A, B, and C have exactly the same 3 elements, so they're the same set. These 2 sets are not equal because this is a set with 1 element, whereas this is just a symbol, not a set. This set has 2 elements, 1, and the set whose only element is 1. And these are the answers for D. Now, a set may contain any kind of elements whatsoever. They need not be the same type. For example, here we have Lady Gaga, pi, and some other numbers. It's a fine set. A set may contain elements that are sets themselves. Here we have a set and another set. So there's 5 elements. Some sets of numbers occur frequently in mathematics, and in discrete mathematics in particular, are shown here. Z is called the integers, but that comes from the German word Zahlen. Rational numbers are quotients of integers, so they stand for quotients, and others are real numbers. You can see down here that the integers, all of these things could be divided by 1, and so the integers are rational numbers. The rational numbers also are real numbers, but there are some real numbers that aren't rational numbers. The square root of 2 is an example. We'll talk about that later. Real numbers can be written on the real number line, and sometimes we use notation of Z with a minus as an exponent to be the negative integers, Q with a plus to be the positive rational numbers, and this non-negative to be the non-negative numbers. If a set is finite, the absolute value of x, or 2 bars on x, in this case, in set theory, equals the number of elements in x. This is called the cardinality of x, and there's also cardinality of infinite numbers, but those are beyond the scope of what we study here. So here is a problem for you to do. You know what to do. Let's see how you did. Well, part A is the numbers between 2 and 5, minus 2 and 5, not including the endpoints. This is another way to say that, and this is another way to say this one. If x is in a set, we write x, and this is the epsilon, but x is an element of x. And if x is not in, capital X, we write x is not in, capital X, or is not an element of that. So 3 is an element of this set, but 3 is not an even number. So 3 is not an element of this set. A set with no elements is called the empty or null set or void set. And the null set is the same thing as writing set builder notations with nothing in them. Two sets are equal, and we write x equal y if they have the same elements. So there's two conditions that x equal y means. For every x that's in capital X, then x is in y. For every x that's in y, it's also in capital X. For a set x to not be equal to a set y, written x does not equal to y, x and y must not have the same elements. There must exist at least one element in x that is not in y, or at least one element in y that is not in x, or both. And we say if every element of x is an element of y, we say that x is a subset of y, and write it this way. Note this allows for the sets to actually be equal. For x not to be a subset of y, there must be at least one member of x that is not in y. Now, it's a consequence of the logic we studied that any set x is a subset of itself, and also the empty set is a subset of every set, because you say if x is an element of the empty set, that's going to be false, so that makes the implication if then true. So if the null set is not a, well, this is just an argument for that. Let's see, if x is a subset of y and x does not equal to y, we say that x is a proper subset of y. And we write this way. Notice this, not allowing it to be equal. The set of all subsets, proper or not of a set, denoted p of x, script p of x, is called the power set. Now, for every element in x, and let's just suppose x has n elements, then each one is independently either in this given subset or not in the given subset. And so if you think about that, and we'll talk about this later, but the power set of a set with n elements has 2 to the n elements. Every element is either in or not in the set. Given two sets, we have operations. We say x union y is the set of x that are x's in x or x's in y. This is an inclusive kind of thing, so if something's in x and y, it's certainly in the union. The set x intersect y is the set of x such that x is in y and x is in x. The set x minus y is the set of elements that are in x and not in y. It's called the difference or relative complement. The difference x minus y consists of all elements in x that are not in y. And finally, we can find the union of a whole collection of sets. The union of a collection of sets is a set of x such that x is in some x where x is one of these collections. And similarly, the intersection of x is x such that x is an element of x for all x in the collection of sets. Sometimes, when we're dealing with sets, all of the sets are a subset of a given set at U. This set is called the universal set or the universe. The universal set must explicitly be given, but sometimes it's just inferred from the context. Given a universal set and a subset of x, the set x minus u minus x rather is called the complement of x and is written as x bar. This is the notation that we will use. Often other books use different notation. So here's a problem for you to do. We let set A be this, set B be this, set C be this, and this is the universal set. You want to list the elements in each set, and I'm going to ask you to do problems 2, 3, 5, 6, 8, 9, 11, 12, 14, and 15. You know what to do. And after the break, we'll continue in lecture 4.1 and see how you did.